Hello everyone. This lecture is exclusively recorded for first year BSc student of BK Birla College, Kalyan. This is mathematics class, calculus paper 2, calculus paper 1. In this paper, we will study the Taylor's theorem and its application. So let me write down the what our aim of this lecture is. Taylor series and applications. So we will state the Taylor's theorem of one variable. Further, we will see some of the examples of Taylor's expansion. So the theorem is as follows. Let f be a real valued function such that the following condition holds. Condition number 1, the n-1th order derivative f n-1th x is continuous on close interval a comma a plus h. Second case, the nth order derivative fnx, that is nth order derivative, exists in a comma a plus h. Number 3, if p is a given point, given positive integer, then there exists theta belongs to open interval 0 comma 1 such that f of a plus h is equal to f of a plus h times f dash a plus h square upon 2 factorial f double dash at a plus dot 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 h raised to n minus 1 upon n minus 1 factorial f n minus 1 at a plus Rn. This Rn is called as a remainder, and what is that Rn? Where Rn is equal to, that is called as a remainder term, and which has a following value. So it is equal to h to the power n 1 minus theta to the power n minus p upon n minus 1 factorial p f nth derivative at a plus theta h. Well, we will not prove this theorem right now, but we will use this theorem for the problem solving. So one thing should be noted: if a is equal to 0, then above expansion is called as Maclaurin expansion. Maclaurin's expansion or Maclaurin series. So Maclaurin series is a special case of Taylor series. When you take it theta, the point a is equal to 0, then the expansion becomes a Maclaurin expansion. So now we'll have some of the example. So find expansion of f of x is equal to e raised to x about x is equal to 0. So solution. So you can see that f dash x being an exponential, it is differentiable. So f dash x is basically e raised to x. Even f double dash x is also e raised to x only. So in general, if you go for any nth order derivative, then fn x is always e raised to x. Now let's find out the remainder term. So okay, so we'll find out the remainder term now. So here we will take p is equal to 1. So you absorb this instead of c. Okay. So in the expansion always we'll have p is equal to 1. That should be noted. Well, I should instead of saying that, I will say if p is equal to 1, then this remainder term is called as a Skolmich. Uh, uh, if p is equal to 1, then Rn is called as Cauchy remainder. And I have one more. So if p is equal to n, if the p value is n, then Rn is called as Lagrange's remainder. So the question is, now we will be, by default when it is not mentioned, we will be applying the Lagrange's remainder. That means we are taking p is equal to n. That should be noted. Okay, so now Lagrange's remainder. For that is Rn is equal to, what is Rn? So h to the power n, 1 minus theta, so n is equal to p, so this is 1, n minus 1 into n, so this will be n into n minus 1 factorial is basically n factorial. This is a is equal to 0. So how does it will look is as follows. So Rn is equal to, now instead of h we will say x. So so we are finding in terms of x. So x raised to n upon n factorial, this is 0. So theta h now bolte we will say theta x. So it will be x raised to n upon n factorial, it will be, because n into n minus 1 factorial will be n factorial, e raised to theta x. Right, and you should note that theta is between 0 to 1. Now we already know that as limit n goes to infinity, x raised to n upon n factorial is always 0. So this remainder term as limit as n goes to infinity, your Rn will go to 0. That one should understand. So if I substitute this all derivatives now in the Taylor series expansion, so substituting this value in Taylor's series expansion, we get what I will get is as follows. So we should go to this f of a, that means f of 0, h, instead of h I will say x now. So f of x is equal to a is 0, h is x, so f of 0 plus x f dash at 0 plus x square by 2 factorial f double dash at 0 and so forth. So this is, so f of 0 plus x is equal to f of 0 plus x times f dash at 0 plus x square upon 2 factorial f double dash at 0 plus dot dot dot. This is an infinite sum since n goes to infinity, so you should have writing this dot 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 infinite series is equally important. But then f of 0, that means f of x is equal to e raised to x. So e raised to 0 is always 1, and hence for all derivatives f dash 0 is 1. So it is 1 plus x square by 2 factorial plus so on and so forth. So we got a expansion for e raised to x. It is summation n goes from 0 to infinity x raised to n upon n factorial. So many a times instead of writing e raised to x, we will write down it as summation n goes from 0 to infinity x to the power n upon n factorial. Okay. Second example, find out the expansion of f of x is equal to sin x about x is equal to 0. So let me calculate f dash x. F dash x is cos x, which is same as sin pi by 2 plus x. F double dash x is minus sin x, which is same as sin of pi plus x. Sin pi plus x is minus sin x. So I will write down 2 times pi by 2 plus x. F triple dash x is minus cos x, which is same as sin of 3 pi by 2 plus x. So if you continue in this way, then f nth derivative of x is equal to sine n pi by 2 plus x for all x belongs to R. So Fn derivative at 0 will be sine n pi by 2. So if I evaluate derivative at 0, then I will have this. Now let's find out the Lagrange's remainder form. So Lagrange's remainder, that is Rn, is equal to x raised to n upon n factorial into f nth derivative at theta x, where theta is between 0 to 1. Now fn nth derivative is basically x raised to n factorial. It is sine n pi by 2 plus x. So theta x, so instead of saying x, it should be theta x. And we know that limit as n goes to infinity, x raised to n upon n factorial is 0, and modulus of this sine n pi by 2 plus theta x, this is also less than 1 for all x. So at the end you can conclude that the limit of Rn is equal to 0. So hence limit of as n goes to infinity of Rn is equal to 0. So if I substitute these all terms in the Taylor series expansion, then I will have f of 0 plus x is equal to f of 0. F of 0 means sine 0. Sine 0 is 0. 0 plus plus. So let me write down the terms in f of 0, then x f dash at 0 plus x square f double dash x square by, it is 2 factorial, f double dash 0 plus x cube upon 3 factorial f triple dash at 0 plus so on and so forth. But you can see that sine n pi, that what is my fnx, it is sine n pi by 2. So when n pi by 2 fn at 0, I should say. Yeah. So the first derivative, when I calculate, then it is sine pi by 2, so that is 1. So this will survive. When I go for n is equal to 2, then 2 will get cancelled. Sine pi is 0, so this will get this, so this will be 0 basically. Then again sine 3 pi by 2, that will be minus 1. Then sine 4 5. So if n is a multiple of 2, then the sine n pi is always 0. And if n is not a multiple of 2, then it will be plus 1 minus 1, it will be alternate. So you will have x, this is first row term is 0 plus x plus this is again 0. Now this is minus x cube by 3 factorial. Then again 0 plus x raised to 5 upon 5 factorial minus so on and so forth. So ultimately we got f of x as x minus x cubed by 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial plus so on and so forth. So at last sin x can be replaced by this summation, n goes from this is minus 1 raised to n x raised to 2n plus 1 upon 2n plus 1 factorial. So n goes from 0 to infinity. So if I replace n is equal to 0, I'll get x, n is equal to 1, 3. Yeah, so that's fine. So sin x can be replaced with this formula. Okay, so similarly one can prove, it's a homework, prove that cos x is equal to 1 minus x square by 2 factorial plus x raised to 4 upon 4 factorial minus x raised to 6 upon 6 factorial plus so on and so forth. In other words, it is summation n goes from 0 to infinity minus 1 raised to n x raised to 2n upon 2n factorial. So, well, this can be done very easily with the help of Taylor series expansion. So, this is what the Taylor series expansion. Of course, there are many more examples which we will discuss in the class. So that's it for the today's. Thank you. Thank you so much.